Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi again, everyone. So we will continue in this video on the example on how to design a PID controller as suggested from the textbook. So I'm using the nice 4th edition control systems textbook. This is example 9.5. So in this example, we have a system that is stable. Okay, we have 3 poles, 1, 0. All the poles are in the left half plane. We need to achieve the transient and steady state specifications. In particular, if you look at number 1, we need to achieve a faster peak time, okay, 2/3 of the uncompensated system peak time. We need to achieve overshoot of 20%, and we also need to achieve zero steady state error for a unit step input. So we will follow the rule or the guideline as suggested in the text, where we will start by achieving the transient specifications using a derivative controller, and then we will add an integral component of the controller. Okay. Okay, so we will look at the specifications where we know the overshoot can be related to the damping ratio, and then the angle. Okay, the angle uh, where the diagonal line will be, if the locus lies on that particular line, then the damping ratio will be constant along that line. So we need to find the line first. Okay, so we got it to be 63 degrees. Next, we can start looking at the locus itself. So the poles and zeros can be marked on the axis. So you can see that I'm using the rule where the locus will lie to the left of odd number of poles or zeros. So here you can see I've highlighted it in yellow portion. That will be the locus, where the locus will lie in the real axis. On the real axis, the locus will lie to the left of odd number of poles and zeros. Okay, this one is easy because the locus will always start from poles and at zeros. So it will just go there. There are no locus this side and this side, and in this case we will assume that it will meet at a certain point in the real axis, and then it will depart. So we need to find asymptote and the breakaway point. So the center of the asymptote has been found using that equation, minus 5.5. So now we need to find the angles of the asymptote. So that's easy. There are just two angles, 90 degrees and 270 degrees. So we can mark it on the complex plane. So next we are going to find the breakaway point, where the locus at starting from minus 6 and minus 3 it will meet at a certain point on the real axis before departing the real axis. So that's called the breakaway point, and I'm going to use the um, KGH expression and substitute S as a real number, and then find the derivative of K with respect to that real number, set it equal to 0, solve for the real number. So we got three roots of that equation that will cause the derivative to be 0. So we know it should be real, and the one we should have selected is minus 4.62. Okay, so that's the breakaway point. Okay, so I've also marked the point where the damping ratio is 0.46. Okay, the angle, okay, where the damping ratio is 0.46, which is 63 degrees line. So now we know that the intersection of the locus with that line is the point where the uncompensated system is performing. So this is the point where we should mark, giving a certain value of overshoot and peak time for the uncompensated system. Okay, in my sketch, it seems that that point is intersects G10, okay, slightly different from the text, but then we can find the real component using the rule of tangent. Tangent 63 degrees is equals to 10 divided by a certain real horizontal length. So 10 divided by this will give the angle of 63 degrees. We can solve for this one, this length, okay, to find the point A, and then we can find the peak time for the uncompensated system. Okay, so the uncompensated system peak time is 0.314. The new peak time, the compensated system, we want it to be at 0.21 second. So you can imagine already that if you just, when you want to achieve a faster peak time, you cannot achieve it because it has to be some, you have to increase the uh, real and imaginary component. If you are just increasing the imaginary component here, then you will not achieve the 20% overshoot. So most likely you will increase the overshoot. So you want to maintain the overshoot, in which case your compensator system should lie along this line. but you also wanted to have a better peak time. So peak time is just pi divided by the imaginary component of the point. So we need to move the locus from the original point A to somewhere here, okay, based on this new specification. Okay, so now we need to find the real and imaginary part of the new point B. Okay, we can obtain it by using the um, requirement of the peak time. Okay, I hope you are following the explanation so far. So we have the new peak time requirements, in which case we can find the imaginary part will give the response peak time, but we also need to achieve the overshoot. So we just use the 60 degrees angle to obtain the real part of the new point. Okay, so you can see here we already achieve, we need to achieve minus 7.68. So the new point will be somewhere here, minus 7.68, 15. So it should be somewhere here along this line. Okay, so you can see point A, and that's the uncompensated system, and then point B. That's the point where we want the response to be after compensation using a PD controller. At this point, let me explain a little bit, because in the previous example, when we sketch and we find a point at a locus, we need to verify whether the point is actually on the locus using the angle criterion. But in this case, because that's not actually the point that we want to find the point B. Okay, anyway, this is just an estimate. So it is here that we want to use the angle requirement to ensure that the point is on the locus after addition of a new zero, and then we will use the magnitude criterion to solve for the k. Okay, so that's why we didn't check whether this point is actually on the locus, but you can do that if you want. Of course, if you have MATLAB, then we know that point A is on the locus because we just drag the cursor and ensure that that point is particularly on the locus. And when design using MATLAB will be covered in a different lecture. So now you can see that I have added a zero here, a real zero, knowing that by adding this zero, then it will contribute to the angle at that particular point. So we want to find where exactly this particular zero that will cause the total summation of the poles and zeros to be multiples of 180 degrees. If you remember the rule on the locus before. Okay, so we need to add up all the angles of the existing poles and zeros, and then the remaining component of the unknown zero will be the one that we need to find, where we are using the angle criterion. Okay, so knowing point B, we have the real and imaginary part of point B here. We just need to find all the angles based on this point. So for example, theta P1 is just tangent of theta P1 is going to be this 15, 10 minus 7.7. We can solve for theta P1 equals to inverse tangent of that ratio. And we repeat for the rest of the angles. And then we solve for this theta Z. Okay, so we got the summation of all the angles. Okay, angles of vector of poles and zeros to the new point, achieving this minus 196.3 degrees. Remember, it has to be multiple of 180 degrees. So we can add a zero contribution to make it as a multiple of 180. So multiple, the closest one is minus 180 degrees. So we just need to find the contribution of 0 so that that one becomes minus 180. So you can see now that the 0 must contribute this angle 16.3 degrees to the total summation in order for the angle criterion to be achieved, which is minus 180 degrees. This 60.3 degrees, you can see this is now not to scale 16.3, so it should be further left. So based on this angle, then you can see we can find the, knowing this point, knowing this angle, then we can find the there's no imaginary part of the 0, so just the real part of the 0 can be found, okay, using the trigonometry. So there you have it, the angle 16.3. So we can solve for x, we can see x is 59, so you can see it's further to the left to give an angle of 16.3 to ensure that this point is indeed on the locus. Okay, now we have found the new zero. Okay, but of course we need to also find the gain that ensures the point is exactly at this 15, 7 minus 7.7 plus 15. So we can use the magnitude criterion, where we need to find the magnitude of all the vectors of poles and zeros and use that to find the value of k. Okay, there's an error here. I just noticed an error. Should be 3 here. Okay, there should be the pole of minus 3. So if you are following this, you want to do it, just change that to the pole. So that's the new point, 7.7. That's the imaginary part of the new point. So that should be 3. But anyway, if the difference are just in terms of 0.1, if I'm not mistaken. Okay, so once we have found the gain key, so we have the PD controller expression, which is 4.47 plus the 0. Okay, now we can go ahead with the requirement number 3 with we need to achieve 0 steady state error. Okay, I've just selected a 0 close to the integrator, the pole S, so that the idea is the 0 and the pole the effect is cancelling out each other, but the positive aspect is we have an integrator to ensure that the steady state error for unit step is 0. Okay, I think the text propose 0.5, but we can try that later using MATLAB. Okay, as long as it's close to the origin, we want to ensure that the I component, the integrator, and the 0 cancels each other, so that it does not disturb much the um, transient response. Um, Transient response as designed by the derivative component of the controller. So that will be the total expression for our PID controller. We have the gain K 4.47, the 0 S plus 59 for the D component, and the S plus 0.1 over S, which is the derivative, sorry, the integral component of our controller. So we can check this later to see whether it really achieved the response that we wanted. So if you check using MATLAB, you manage, if you're using these values, you will achieve the damping ratio of 0.46, but we just look at the overall response using the compensated system, and we can compare with the uncompensated system. Okay, so we can use MATLAB to check our answer. The system uncompensated is given here. This is a small MATLAB script which you can obtain later using the link below. So the notes and the MATLAB script, you can just leave your name and email, and these notes and MATLAB script will be emailed to you later. Alright, so this is the uncompensated system. That's the compensated system with just PD, and then there's the PID. So we can see the response. So the uncompensated is blue, the red is the PD compensated, whereas the green is the PID compensated. There you go. So that's the uncompensated system. That's the PD compensated system, which is the red. Okay, that's the PD. So you can see that the response has less steady state error, but better peak time. Okay, peak time is 0. We require it to be 0.21 if I'm not mistaken. And then for the case when we use the 0.1, this is what we achieve. Okay, the steady state error is almost 0. You can play around with the effect of the 0 on the I component. So for example, here I change to the one as suggested in the text to 0.5. You can see it performs even better. Okay, as a steady state much faster, right? So you can play around with the MATLAB script to see the different response for the different zeros and bow. For example, if you want to change the PD and PI component. Okay, everyone, I think that's all for this video. Thanks for watching. If you want to have the MATLAB script and the notes, the sketch of the root locus and the notes that I use in this video, please leave your name and email. You will get it through email later. Thank you, everyone. See you again. Assalamualaikum warahmatullahi wabarakatuh.